Imagine standing on a launch pad in Florida, watching the most powerful rocket ever built rise into a blue American sky. The countdown hits 0, engines ignite. The ground shakes beneath your feet. Millions of pounds of thrust lift a small capsule carrying human beings toward the red planet. The world cheers. Headlines declare the dawn of a new era. The first humans are going to Mars. But buried beneath the celebration is a truth no one wants to say out loud. For the first generation who go, there may be no coming back. Not because we can't land there, not because we can't survive for a while, but because the physics of interplanetary travel, the brutal mathematics of rocket fuel, and the slow, irreversible changes inside the human body may quietly close the door behind them forever. A mission to Mars is not like flying to the moon. It is not a 6-day journey with a quick return home. It is a multi-year commitment to a world where the air is poison, the gravity is weak, the radiation is relentless, and Earth is nothing more than a pale blue star in the sky. Tonight, we are going to explore why anyone who goes to Mars may never come back, and why the first pioneers won't just be astronauts. They will be immigrants. The first permanent citizens of another world. If you enjoy deep, slow journeys like this through the realities of space exploration, take a moment to subscribe, like the video, and leave a comment. And here's your comment task for tonight. Tell us which part of the United States you're watching from. Are you in California, Texas, New York, somewhere in the Midwest, or along the East Coast? It's incredible to think that while we talk about leaving Earth, millions of us are scattered across one nation under the same sky. Now take a slow breath. Let's begin. The dream of Mars has been part of American imagination for generations. From the early days of NASA during the Apollo era to modern private space companies launching reusable rockets, Mars has always been the next horizon. It is close enough to feel attainable, yet distant enough to represent true interplanetary travel. Unlike the Moon, which is a 3-day journey away, Mars sits tens of millions of miles from Earth. At its closest approach, Mars is about 54.6 million kilometers away. At its farthest, it can be over 400 million kilometers distant. That variation is not random. It is dictated by orbital mechanics, the invisible geometry of two planets circling the Sun at different speeds. Earth completes one orbit around the Sun every 365 days. Mars takes about 687 Earth days to complete its orbit. Because of these differing orbital periods, the distance between Earth and Mars constantly changes. The optimal time to launch a mission to Mars occurs during what is called a launch window, when Earth and Mars are aligned in such a way that a spacecraft can follow a Hohmann transfer orbit, the most fuel-efficient path between two orbits. These launch windows occur approximately every 26 months. Miss the window and you wait more than 2 years for the next opportunity. This alone traps you. If you travel to Mars, you cannot simply decide to return whenever you feel ready. You must wait for the planets to align again. A typical Mars mission profile involves about 6 to 9 months of travel to reach Mars, roughly 500 days on the Martian surface waiting for the next launch window, and then another 6 to 9 months traveling back to Earth. That is nearly 3 years in total. Even in the most optimistic scenario, returning home requires patience measured not in days or weeks, but in planetary alignments. Now consider what that means. If something goes wrong during your stay on Mars, there is no rescue ship that can launch tomorrow. There is no emergency evacuation system standing by. The fastest possible rescue mission would still require months to reach you, and only if the launch window is open. For much of your stay, Earth and Mars will be positioned in such a way that any return would require enormous amounts of fuel far beyond practical limits. In some parts of the orbital cycle, Mars and Earth are on opposite sides of the Sun. Communication signals must travel around the Sun, introducing delays and interference. Speaking of communication, even at their closest approach, radio signals take about 4 minutes to travel one way between Earth and Mars. At their farthest separation, that delay grows to about 24 minutes one way. That means a round-trip communication delay of up to 48 minutes. If a system fails, if someone is injured, if a life support alarm goes off, you cannot call Houston and receive immediate instructions. You send a message, wait nearly half an hour, receive a response, and then act. Mars colonists will not have real-time conversations with Earth. They will live in delayed isolation, psychologically cut off from immediate human support. But distance and communication delay are only the beginning. The deeper challenge lies in physics, specifically the rocket equation. In the early 20th century, Russian scientist Konstantin Tsiolkovsky formulated the mathematical relationship that governs how rockets move. The equation shows that to achieve higher velocities, a rocket must carry exponentially more propellant. It's not a linear relationship. If you want to double your change in velocity, you need far more than double the fuel. Every additional kilogram of propellant adds mass, and that mass itself must be accelerated, requiring even more propellant. To land on Mars, you must first launch from Earth's deep gravitational well. Earth's escape velocity is about 11.2 kilometers per second. Reaching orbit requires traveling at roughly 7.8 kilometers per second. Escaping Earth entirely requires even more energy. That alone demands enormous rockets like NASA's Space Launch System or private heavy lift vehicles currently under development. But here's the crucial point: landing on Mars is only half the journey. To return, you must launch again, this time from Mars' surface. Mars has lower gravity than Earth, about 38% of Earth's gravity, which helps. Its escape velocity is around 5 kilometers per second, significantly lower than Earth's. But even so, launching from Mars requires a fully fueled ascent vehicle waiting on the surface. And how does that ascent vehicle get there? If you bring return fuel with you from Earth, you must launch that fuel from Earth in the first place. That dramatically increases the mass of your initial spacecraft. More mass means more fuel to leave Earth. More fuel means even more mass. The rocket equation compounds the problem. A round-trip Mars mission could require 5 to 10 times more launch mass than a one-way mission, depending on mission architecture. That translates to billions of dollars in additional cost and significantly greater engineering complexity. This is why many serious mission planners talk about in-situ resource utilization, or ISRU. Instead of bringing all return fuel from Earth, astronauts would manufacture fuel on Mars using local resources. The Martian atmosphere is mostly carbon dioxide. With sufficient energy, carbon dioxide can be processed into oxygen and methane, the propellants proposed for many modern rocket designs. Water ice, known to exist beneath the Martian surface and at its poles, can be split into hydrogen and oxygen through electrolysis. The concept sounds elegant. Land an automated system on Mars years before the crew arrives. That system produces fuel and stores it in tanks. When astronauts land, their return fuel is already waiting for them. But this introduces enormous risk. If the ISU system fails, the astronauts cannot leave. There is no backup refinery on Mars. There is no quick resupply mission. The first crew would essentially be trusting their lives to machines that must operate flawlessly for years in a hostile environment before humans even arrive. And Mars is hostile. Its atmosphere is about 95% carbon dioxide, with a surface pressure less than 1% of Earth's. If you stepped outside without a spacesuit, you would lose consciousness in seconds. The average surface temperature is around -80 degrees Fahrenheit, with nighttime temperatures near the poles dropping to -195 degrees Fahrenheit. Dust storms can envelop the entire planet for weeks, reducing sunlight and threatening solar power systems. Radiation presents another silent danger. Unlike Earth, Mars does not have a global magnetic field. Earth's magnetosphere deflects charged particles from the Sun and cosmic rays from deep space. Mars lost its global magnetic field billions of years ago. As a result, its surface is exposed to higher levels of radiation. During the 6 to 9 month journey through interplanetary space, astronauts would also be exposed to cosmic radiation without Earth's magnetic protection. Over a 3-year mission, cumulative radiation doses could approach or exceed current NASA career limits for astronauts, increasing the lifetime risk of cancer, cardiovascular disease, and neurological damage. Now consider the human body in low gravity. Mars' gravity is only 38% of Earth's. That may sound manageable. It is more than the Moon's gravity, which is about 16% of Earth's, but we have never observed humans living for years in partial gravity. On the International Space Station, astronauts in microgravity experience bone density loss of about 1 to 2% per month without countermeasures. They exercise for hours daily to mitigate muscle atrophy and bone loss. Even so, some effects persist after returning to Earth. On Mars, gravity is not zero, but it is significantly lower than what our bodies evolved under for millions of years. Bones remodel themselves in response to mechanical stress. Reduce that stress and bone density declines, muscles shrink. The cardiovascular system adapts to pumping blood in a lower gravity environment. Over years, these adaptations may become semi-permanent. An astronaut who spends 3 years in transit and on Mars could return to Earth severely weakened, struggling to stand under full gravity. But what if the mission extends beyond 3 years? What if the first settlers remain for a decade, or for life? The longer a human body adapts to Martian gravity, the more difficult it may become to readapt to Earth's gravity. There is a possibility that after long-term habitation, returning to Earth would be medically dangerous, perhaps even impossible without extreme rehabilitation or artificial gravity training. And then there is psychology. Isolation, confinement, and distance from Earth create unique stresses. Antarctic research stations provide some insight. Crews overwintering in Antarctica report mood disturbances, sleep disruptions, and interpersonal tensions. But Antarctica is still on Earth. Rescue is possible within days or weeks. On Mars, you are millions of miles away. You look up at the sky and see Earth as a small star. You know that any emergency response is months away, if it is possible at all. The first Mars settlers will not simply be astronauts completing a mission. They will be pioneers accepting permanent separation from Earth. Even if a technical return is planned, the cumulative effects of time, gravity, radiation, and resource constraints may quietly convert a temporary stay into a permanent relocation. And what about children born on Mars? If a settlement grows and families are formed, a child raised in 38% gravity may develop differently. Their bones might grow longer and thinner. Their muscles may adapt to lower loads. Their cardiovascular system may be tuned for a weaker gravitational pull. If such a person attempted to travel to Earth, the sudden exposure to full gravity could be overwhelming. Their skeleton might not support their weight. Their heart might struggle to pump blood effectively. It is possible that the first generation of Martian-born humans would be biologically unable to ever live on Earth. At that point, Mars is no longer a destination. It is a divergence, a branch in human evolution. So when we ask why anyone who goes to Mars may never come back, the answer is layered. Orbital mechanics trap you for years. The rocket equation makes return fuel exponentially expensive. In situ resource utilization systems introduce life or death dependencies on fragile infrastructure. Radiation and low gravity slowly alter your biology. Communication delays isolate you psychologically. And over time, the red planet ceases to be a temporary assignment and becomes home. The first Mars missions will be framed as exploration. Flags will be planted. Speeches will be made. But beneath the symbolism lies a deeper truth. They will be colonization missions. The first crew will carry not just scientific instruments, but the weight of permanence. They will build habitats, refine water, generate oxygen, grow food in artificial soil. They will learn to survive dust storms and equipment failures without immediate help. They will adapt their bodies and minds to a world fundamentally different from Earth. Returning home may remain technically possible for some, but practically, economically, biologically, and psychologically, it becomes less likely with every passing year. Mars does not just demand courage. It demands commitment, a willingness to trade blue skies and oceans for red horizons and manufactured air, a willingness to accept that the distance between planets is not just measured in miles, but in years in radiation exposure, in altered bones and hearts. A small habitat on a cold Martian plain. Outside, the sun sets as a pale disk through thin, dusty air. Inside, a human being looks at a photograph of Earth, oceans, forests, cities glowing at night. 40 million miles away at closest approach. 400 million at farthest, reachable in theory, but in reality, separated by physics, fuel, and the fragile limits of the human body. Let's begin with gravity again, but this time stretch it across decades instead of months. On Earth, every system in your body evolved under one constant force, 1G. Your bones are dense because they must hold you upright. Your leg muscles are strong because they resist gravity with every step. Your heart pumps against a vertical column of blood. Your inner ear balances your posture against a consistent downward pull. Remove that force, and the body adapts. We have decades of data from astronauts in orbit showing that even with rigorous exercise, bone mineral density declines in microgravity. Muscle mass decreases. The heart slightly reshapes because it no longer has to work as hard to pump blood upward. Vision can even change due to fluid shifts toward the head. Mars is not microgravity, but it is not Earth either. At 38% of Earth's gravity, your body is carrying far less weight. You would feel lighter. You could jump higher. Heavy equipment would feel easier to move. At first, it might feel liberating. But over years, your skeleton might thin in response to reduced load. Your muscles would not need to generate the same force. Even if colonists exercise daily in resistance gyms, It is unlikely they could perfectly simulate Earth's gravitational stress 24 hours a day. Over time, their bodies would tune themselves to Mars. Now imagine returning after 10 or 15 years. You land back on Earth. The hatch opens. You attempt to stand. Suddenly your body weighs nearly 3 times what it did on Mars. Your heart must pump harder. Your bones must support far greater load. The simple act of walking feels like wading through invisible cement. Rehabilitation might take months, perhaps years. Some damage could be irreversible. The very adaptation that allowed you to thrive on Mars becomes a liability on Earth. Radiation compounds the problem. During the journey to Mars, astronauts are exposed to galactic cosmic rays and solar particle events. These are high-energy particles capable of penetrating spacecraft hulls and damaging DNA. On Earth, we are shielded by both our atmosphere and magnetic field. On Mars, there is no global magnetosphere and the atmosphere is thin. Colonists will need to live in habitats shielded by thick walls of regolith, possibly buried underground to reduce exposure. Even so, cumulative radiation over years may increase cancer risk, affect cognitive function, and potentially impact reproductive health. The 3-year round trip already pushes NASA's acceptable lifetime radiation limits. Extend that to permanent settlement, and you are talking about exposure levels humanity has never experienced continuously. Returning to Earth does not undo radiation damage. It travels with you in the form of altered cells and increased long-term risk. The decision to go to Mars is not just a career move. It is a medical gamble. Then there is the closed-loop life support reality. On Earth, air is free. Water falls from the sky. Food grows in soil enriched by billions of years of biological cycles. On Mars, every breath you take is manufactured. Oxygen must be extracted from carbon dioxide or produced by splitting water molecules. Water must be recycled with extreme efficiency. On the International Space Station, astronauts recycle urine into drinking water through advanced filtration systems. A Mars colony would need similar systems, but scaled for larger populations and long durations. If a life support system fails on the ISS, rescue is days away. On Mars, rescue is months away if possible at all. Every pump, every valve, every filter becomes a critical component. Redundancy will be built in, but redundancy adds mass, and mass increases cost. Colonists will need to become engineers, technicians, farmers, doctors, and problem solvers simultaneously. Survival will not be a passive state. It will be an active, daily effort. Food production introduces another layer. Early missions may rely on packaged supplies from Earth, but permanent settlement requires local agriculture. That means controlled environment farming under artificial light or filtered sunlight. Crops must grow in processed Martian soil or hydroponic systems. Nutrient cycles must be carefully balanced. A fungal outbreak, a crop disease, or system malfunction could threaten the entire colony. On Earth, agriculture failures are devastating but geographically limited. On Mars, a crop failure in a sealed habitat is existential. Now consider emergencies. A medical crisis on Earth is met with ambulances, hospitals, specialists, blood banks, advanced imaging, and rapid communication. On Mars, the medical facility will be small. Surgical capability will be limited. If someone suffers appendicitis, a traumatic injury, or a complex infection, the crew must handle it themselves. There is no medevac flight to a better equipped hospital. Communication delays prevent real-time guidance from Earth-based surgeons. Artificial intelligence may assist, but it cannot replace decades of human surgical experience in unpredictable conditions. Mental health may prove equally challenging. Humans evolved in open environments under blue skies surrounded by natural ecosystems. Mars offers rust-colored plains, a butterscotch sky, and confinement inside habitats for protection. Even if virtual reality systems simulate forests or oceans, colonists will know they are simulations. The knowledge that stepping outside without protection means death creates a constant psychological boundary. Over time, monotony, isolation, and the absence of natural Earth stimuli could affect mood and cognition. Yet perhaps the most profound shift occurs over generations. Imagine a child born inside a Martian habitat. That child has never seen an ocean, never felt rain, never breathed unfiltered air. Their concept of outside is a hostile desert under a thin sky. They learn to walk in 0.380 g. Their bones grow under reduced load. Their muscles develop differently. They look at Earth not as home, but as an ancestral world, a distant origin story. If that child grows into adulthood, would they even want to visit Earth? And if they did, could they survive the gravity? Their cardiovascular system, skeletal density, and overall physiology might be fundamentally tuned to Mars. Returning to Earth could require months of conditioning in artificial gravity environments before even attempting landing. Some scientists speculate that a Martian-born human might experience severe health complications in full Earth gravity. In that scenario, the separation between Earth and Mars becomes not just cultural, but biological. At that point, the phrase, "never come back," takes on new meaning. It is not just about mission design or fuel constraints. It is about divergence. The first Mars settlers may accept that they are the beginning of something new, a branch of humanity adapted to a different planet. Economics reinforces this permanence. A single crewed Mars mission could cost tens or hundreds of billions of dollars. Launching return vehicles, maintaining fuel production infrastructure, and sustaining long-term support from Earth requires enormous ongoing investment. Governments and private companies may initially support round trips for demonstration missions. But once a settlement exists, economic logic may favor one-way expansion. It is cheaper to send supplies and new settlers than to fund return flights for every individual who changes their mind. The narrative will shift. Instead of astronaut returns home, it becomes pioneer establishes new life. The cultural expectation evolves. Volunteers for Mars will understand that they are emigrating, not touring. Like settlers crossing oceans centuries ago, communication with home will be slow. Return will be rare. And yet, this is not a story of doom. It is a story of transformation. Humanity has always expanded into environments that seemed impossible. Crossing the Atlantic in wooden ships once meant months at sea with no guarantee of survival. Settling the American frontier required leaving familiar cities behind. The difference with Mars is scale. The ocean between Earth and Mars is not water. It is vacuum. The storms are not waves. They are radiation bursts and dust storms. The isolation is measured in millions of miles. The first Mars missions will be framed as exploration, but they are more accurately described as the first act of planetary migration. Once a self-sustaining colony exists, it will gradually reduce dependence on Earth. Manufacturing will develop locally. Energy systems, perhaps nuclear reactors or vast solar arrays, will power habitats. Mining operations will extract water, ice, and minerals. Over decades, the colony may become economically and culturally distinct. Communication delays will shape governance. With up to 48 minutes round-trip delay, real-time political control from Earth becomes impractical. Mars settlements will need local decision-making authority. That autonomy further cements separation. The psychological identity of being Martian will strengthen with each generation. So when we ask why anyone who goes to Mars will never come back, the answer unfolds in layers. Orbital mechanics delay departure for years. The rocket equation makes round trips exponentially more expensive than one-way missions. Manufacturing return fuel on Mars introduces life or death technological dependencies. Radiation and low gravity alter human biology in ways that may be irreversible. Communication delays isolate colonists from immediate support. Children born on Mars may be physically unable to thrive on Earth. Economic realities favor permanent settlement over repeated returns. Individually, each factor is challenging. Together, they form a web that gently but firmly holds settlers in place. Picture a habitat dome glowing softly against the Martian night. Inside, people share meals grown in hydroponic farms. They celebrate birthdays under artificial light. They look at Earth as a bright star in the sky. For some, the idea of returning may remain a dream. For others, it may no longer matter. Their friendships, their work, their families are on Mars. Home becomes a definition shaped by presence, not origin. The first generation will carry memories of blue oceans and green forests. They will feel the ache of distance most strongly. The second generation may feel curiosity about Earth, but not homesickness. The third generation may view Earth the way we view ancient homelands, important but not central to daily life. And so the journey to Mars is not simply a mission. It is a crossing, a threshold. The moment humanity stops being confined to one planet and accepts the cost of spreading to another. There will be heroic launches. There will be flags planted in red soil. There will be speeches about exploration and progress. But beneath it all lies a quiet understanding. The first pioneers are not just traveling. They are relocating. They are trading one gravity for another, one sky for another, one world for another. And once that trade is made, once bodies adapt and societies form and children are born under a salmon-colored sky, coming back may no longer be possible, practical, or even desirable. Mars will not just change those who go there, it will keep them.